Okay, geometry students, in this video we will be studying the topic of symmetry. Now hopefully you will remember using this word when you graphed parabolas in algebra. Your heading today is symmetry. I would like you to write that down, please. The lesson number is 1.4, so also copy that in your notes if you would, please. And also include, sorry about that, and also include today's date, okay? So the heading is symmetry. The lesson number is 1.4, and please include today's date. A figure, please write this down. Whenever you see an asterisk in these videos, that means the following phrase is test-worthy or quiz-worthy, or both. So please write this down. A figure is said to have line symmetry or reflection symmetry if the figure can be divided into two parts that are a mirror image of each other. Please copy that down. I'm going to continue on, but you can still copy this down. A picture always helps. So if this phrase up here did not make a lot of sense to you, that's okay. Let's look at some examples that might actually help you understand what line symmetry or reflection symmetry is. Okay, you can copy these down one at a time. Let's go ahead and start with this figure here. Please copy down a triangle in your notes that looks like this right here, please, if you would. Now it's very easy to see that this triangle does have line symmetry. In fact, we would say this triangle right here has vertical line symmetry. Vertical line symmetry. My handwriting is not the best, but you can write that down. Vertical line symmetry. And here's how I know that. If you were to draw an imaginary line right down the middle of this triangle like this, and you were to fold the triangle over on top, fold the triangle on this line. If you were to fold this triangle in half and fold it right on this line, this triangle right here that I'm going to highlight in red, right here, would fall right on top of this triangle here that I'm highlighting in green. Do you see that okay? So if that happens, then you know you have symmetry. It's that easy, students. It's really not that difficult. Now, when I take a look at this figure right over here, and let me quickly get rid of this one so we have more space, go ahead and copy this triangle in your notes if you would, please. Now, I don't care where you draw a line on this triangle. There is no line you can draw anywhere that if you fold the triangle on that line, that it will fall directly on top of the other side of the triangle. It's just not going to happen. If you drew a line here, there's no way this little triangle here is going to fall on top of this big triangle over here. If you were to take the triangle and turn it a little bit, maybe turn it this way, like this, there's still nowhere you can draw a line in which if you were to fold the triangle on that line, the two triangles would fall, or the two sides, I should say, would fall right on top of each other. It's just not possible, okay? So this triangle here would not have line symmetry at all. Now this is what we call an ellipse. Go ahead and draw this in your notes if you would, please. And I would like to submit to you that this ellipse has vertical line symmetry. Please write that in your notes. But it also has horizontal line symmetry, and I would write that in your notes also. Okay, it has both, because look, if I drew a line right through here, a horizontal line, and then folded the ellipse right on this line, this side of the ellipse right here would fall right on top of this side of the ellipse over here. I think that's pretty obvious. And also, if I draw a vertical line like this, that would also work, because if I folded the ellipse right on this line, we can see that this side right here would fall directly on top of this side over here. I hope that makes sense. And that's when you have symmetry, okay? A figure is said to have line symmetry or reflection symmetry if the figure can be divided into two parts that are a mirror image of each other, okay? And then referring back to Algebra 1 or Algebra 2, like I did earlier at the beginning of this video, you see a parabola right here, and you should remember these from Algebra 1 and Algebra 2 both. And remember, all parabolas had what we called an axis of what? Do you remember? An axis of symmetry. And it was called an axis of symmetry because it was an imaginary dotted line that went right through the vertex on the parabola, And the reason it's called an axis of symmetry is if you were to take the parabola and fold it over on this dotted line, this part of the parabola here would fall right on top of this part of the parabola over here. Okay, so it should be somewhat familiar to you. Okay, well, let's continue on. Here we go. Let's look at some more difficult examples. Now, you don't need to copy these figures down. Just do this in your notes. Okay, in your notes, just write this. Okay, write this down. Write page 22. Write that in your notes, please. Example number 1. Okay, write that in your notes. And then we're going to take some notes about A, we're going to take some notes about B, and we're going to take some notes about C. But there's no need to waste class time and copy all of these figures down. Okay, so we're not going to worry about that. Just write down page 22, example number 1, and let's go ahead and get started. All right, identify the lines of symmetry in the figures. Well, I hope you can see, students, that there is no way you could draw a vertical line anywhere, so that if you folded this lobster, I guess it is, if you folded this lobster on any of these lines, there's no way that each side would fall on top of the other side exactly. However, we do have a horizontal line of symmetry right here down the middle. And of course, we're not, as a teacher, on your tests and quizzes, I'm not expecting you to measure the length of this little part here and make sure it falls exactly over here. We're not looking at that. We're just saying, in general, is the object symmetrical? And this is, letter A, if you want to take notes on this, has a horizontal, I'm going to put HL from here on to save time. It has horizontal line symmetry. Okay, and if you were to fold the lobster right on that line, this side over here would fall right on top of this side over here. Okay, let's take a look at letter B. Now, this object here in letter B has horizontal line symmetry, and it also has vertical line symmetry. Okay, if you were to draw a vertical line here and fold the object right on that line, this side right over here would fall right on top of this side over here, as you can see. And if we drew a horizontal line and folded the figure on that line, this side right here would fall right on top of this side over here. Okay, and so we have horizontal line and vertical line symmetry. Now here it might look like we have infinite amounts of symmetry. I mean, here and here and here, but actually figure C has no symmetry at all. And before you panic, let me explain why. Okay, no symmetry. You might say, well, Mr. Earhart, that's not true. If I drew a vertical line right here and I folded this side of the circle right here, right on top of this side over here, then they would be symmetrical. Now, hold on a second. Yes, we don't have to worry about colors. That's true. Colors do not matter. However, the lines do. And look at this little line right here. If you were to fold it over, there's no line over here right here for this line right here to fall on top of. Look down here at the bottom. Do you see this little line from here? Well, not a line, but this arc from here to here. If you were to fold the circle right on this vertical line and this arc right here fell over here, there's no arc for it to fall upon. Okay, and so we really don't have symmetry. No matter where you draw a line on this circle, you will not have symmetry. You can go ahead and practice them if you want to whenever you get a chance later, but you will see there's no symmetry at all for this circle. It would not work. Now, if this line right here, and once again, I shouldn't call it a line, if this S-looking shape was not here, then I would say, okay, then we could have a lot of lines of symmetry, because everywhere you would draw a line that passes through the center of the circle would be a line of symmetry. But we do have this line right here, this black squiggly line right here, and so it does complicate things. Okay, so there's some more difficult examples of trying to see if a figure has symmetry or not. Now let's continue on. Let's look at a topic that's a little more difficult. Let's look now at another type of symmetry called rotational symmetry. Now, if you'll take really good notes and pay attention, you'll be fine, but you're going to have to pay attention. This can be difficult, okay? So this can be confusing. Please pay close attention and take really good notes. Rotational symmetry, notice the asterisk. Please copy this in your notes, all right? When a figure is rotated 180 degrees or less, and at any point during the rotation it coincides with the original figure, then we have rotational symmetry. Okay, So, rotational symmetry exists when a figure is rotated 180 degrees or less, and at any point during this rotation, it coincides with the original figure. Now, once again, like the previous definition I gave you, these definitions can be tough to understand. So, let's again use pictures to help us understand what rotational symmetry is. All right, here we go. Let's go back to one of the figures we just looked at a couple minutes ago. And you know what? Go ahead and copy this in your notes if you would. Real quick, go ahead and draw a circle like this, and then draw a squiggly line like this. It doesn't have to be perfect, that'll be good enough, okay? Now, on a test or a quiz, please listen to me carefully, students. On a test or a quiz, when I give you an object and I say to you, does this object have rotational symmetry? The best thing for you to do, now listen to me, is take a sheet of paper and put it on top of the object and trace it. And then pull the sheet of paper over here, okay? And then take that sheet of paper and, hold on one second please, take that sheet of paper and just rotate it slowly until you've rotated 180 degrees. Now 180 degrees would be half of a circle and no more. At any time during that rotation, if the figure looks like the one you started with, then you have rotational symmetry. And again, color does not matter, we're just looking at the lines. So with that in mind, here's what I'm going to do. I'm going to go ahead and in your notes, you can just kind of watch here or take notes however you want to. But I went ahead and I copied this. All right, there we go. Now, I'm going to see if at any time as we rotate this, do we have symmetry, or do we have a figure that coincides with the original? So here we go. I'm going to take this and start turning it, okay? Now remember, when I say coincides with the original, we're not looking at the colors, just the lines, okay? And let's review. Remember, this figure here did not have symmetry. It did not have line symmetry. Okay, let's see if it has rotational symmetry. You're going to see that it does actually. So here we go. Now remember, I go no more than 180 degrees. So I rotate from here to here and I'm done. Okay, so here we go. I'm going to start here. Hopefully you're not getting dizzy there. And I'm going to start rotating this. Let's see if it ever looks like the other side. We're not worried about colors, just the lines. So far it doesn't look like the original. Does not look like the original. Does not look like the original. Not yet. But right there it is. Right there. At 180 degrees, look at the lines. I think I went maybe a little too far. No, that's perfect. So notice I have this object here. Looks just coincides, means an identical object. I have this right here. Notice this line here starts here and goes like this and goes like this. Notice the line starts here, goes like this and goes like this. So there we go. If I can take an original figure and rotate it 180 degrees or less, and at any point along that rotation the figure looks like the original figure, then I have rotational symmetry. Now I know one example is not enough, so let's try a couple more. All right. Again, there's no need to copy these figures in your notes. It just takes time. What I'd like you to write in your notes is page 23, example number 2. That's what I want you to write in your notes. Write page 23, example 2. All right, then we're going to talk about A, B, and C. Now these are going to be difficult to take notes on because you're going to have to maybe draw some things or take some side notes, but you're big juniors and sophomores, so I will let you guys figure that out on your own. Okay, let's see if figure A has rotational symmetry. All right, so here we go. The first thing you do on a test or a quiz when I ask you that is trace the figure over, so you have a picture of it, excuse me. And now let's go ahead and start rotating it, and let's see if it ever looks exactly like the original figure. So here we go. Not yet. Pointing down. Not yet. Not there. No, not quite. Not there. And to here. And actually, students, I'm going to have to correct myself here, although to be honest with you, I kind of feel like when I took a picture of this from the book and kind of moved it over, it just doesn't look very much like the original picture, but that's okay. Okay, here we go. We rotate it like this, okay? Now it doesn't look like the original picture yet, still doesn't, and right here it's supposed to. Now if you'll look in your book, you'll see that to me it doesn't, but I think somehow when I copied this, maybe I stretched it a little, or maybe somehow I didn't take a very good picture of it from the book, but that's okay. We're just going to use our imagination, if it's okay with you, and just see how this is supposed to look like the original triangle. It really is. If you'll look in your book, you'll see that they do a better job of of turning it than I've done. Now I want to show you about how many degrees we rotated, okay? Now everyone should know if you start here and go all the way half a circle, that's 180 degrees, okay? So if we start here and go 1/4 of a circle, that should be 90 degrees. So we started here. We started here and we rotated 90, and we still did not have a figure that coincided with the original figure. So we had to keep going, and that looks like about 30 more, maybe, something like that, around 30. So that would be about 120 degrees approximately, and I'm not going to make you measure it exactly, but you can see we rotated 90 degrees and then about 30 degrees more. So we're going to say that A does have rotational symmetry after about 120 degrees of rotation. Okay? All right. Now let's come up here and let's try another one. All right? Let's grab this one right here. And remember, on a test or a quiz, I would want you to copy it onto a sheet of paper, and like this. And now let's start turning this, and let's see if it ever looks like the original figure. Okay? I don't think it's going to at all. Okay, it does not look like the original figure. Not yet. Not yet. Not yet. Not yet. And no, it never does. I rotated at 180 degrees, and at no point did this figure right here ever look like the original figure over here. So this figure right here, letter B, does not have rotational symmetry, okay? And let's quickly take a look at the last one, then we'll move on to another topic, and we'll be done after some examples here, okay? All right, so this is letter C. And the first thing you want to do if you're taking a test or a quiz is put a piece of paper on top of the figure and copy it, and then take your sheet of paper and turn it and see what happens, okay? And let's see. When will it look like identical to the original figure over here? Well, I'm turning right there. It's supposed to, okay? Now, again, I think somehow I've stretched these a little bit maybe when I took the picture, but if you'll look in your book, you'll see they do a little better job. But there's one at 90 degrees, and then if I continue on, again, at 180 degrees, we have a figure here that coincides with a figure over here. Okay, so yes, we do have rotational symmetry of this figure, and it happens at two different places. It happened at 90 degrees, and it also happened at 180 degrees. Okay, so let me repeat this again. You rotate the figure and look to see if the figure ever coincides exactly or looks exactly like your original figure as you rotate it up to 180 degrees. Okay, I hope that makes sense. That's called rotational symmetry, and you need to be familiar with that. All right. Lastly, let's finish up the video with a topic you should be familiar with, and that is finding the midpoint between two given points. Now here's the formula, so please copy this into your notes. Midpoint formula equals, or midpoint equals, x plus x divided by 2, and then a comma, and then y plus y, excuse me, y plus y divided by 2. All right, let's continue on. It is really a simple process in which you add two numbers together and divide by 2. For example, and don't write this down, just listen. If you had an 80 and a 90 on two tests, in order to find the average or the midpoint between these two tests, the middle between these two tests, you would simply add the two tests together, would you not? And divide by 2. And if you added 80 and 90 together and divided by 2, what average would you get? 85. And is that not right in the middle of 80 and 90? Sure it is. And that's why we add two numbers and divide by 2. It's like finding the average or the midpoint. Okay? All right, let's continue on. That is exactly what we are going to do to find the midpoint between two given points. Let me show you. Now, I'd like you to copy this in your notes, please. I want you to find the midpoint between these 2 points. So pretend you had the point plotted on a coordinate plane, 7, 4, and pretend that you had this point plotted on a coordinate plane, 1, -2, and I wanted you to find the point right between them. Well, according to this formula right here, we're going to add our 2 x's and divide by 2, add our 2 y's and divide by 2. So here we go. This is my x, this is my y, this is my x, this is my y. So I would have 7 plus 1, those are my 2 x's, 7 and 1. So 7 plus 1 divided by 2, and then put a comma, And then here's my y, a 4. Here's my y, a -2. So I would have 4 plus a -2. 4 plus a -2 divided by 2. And if you quickly simplify that, you would get 4 comma 1, because 7 plus 1 is 8. 8 divided by 2 is 4. 4 plus a -2 is 2, and 2 divided by 2 is 1. Now let's real quick see if that makes sense. Okay, let's just see if that looks right. So very quickly, I'm going to plot the point 7, 4. 1, 2, 3, 4. And you don't need to do this if you don't want to. I'm just going to do it to show you something. 7, 4. So there's the point 7, 4. Here's the point 1, -2. So there's my two beginning points. Now this midpoint right here should fall right in the middle. Over 4, up 1. Not quite in the middle, but remember, my drawing's not perfect. It's pretty close to the middle, okay? So 4 comma 1 is the midpoint between these 2 points right here. Now let's take a look at another problem. I would like you to quickly graph this if you would. I want you to get used to looking at graphs and find midpoints. So quickly draw a coordinate plane. I want you to plot the point -3, 1 and plot the point 2 comma 2. Okay, I'm going to wait just about 30 seconds while you do that. Quickly put this line segment graph into your notes if you would please, and then we're going to find the midpoint between these 2 points. If you want to draw this and then continue on and work without waiting for me, that's totally fine. If you want to wait for me, that's fine also. Okay, here we go. Let's find the midpoint between these 2 points. Well, we know that it's x plus x divided by 2 and y plus y divided by 2. So my one x is -3, my other x is 2 over 2, comma. My one y is 1, my other y is 2, and so 1 plus 2 over 2. All right, and then finishing this up, -3 plus 2 is -1, and -1 over 2 would be a -1/2. You could put -0.5, but I really don't want decimals on tests and quizzes. I like to have exact numbers, which means fractions, improper, or mixed numbers either way. Okay, so -3 plus 2 is -1, -1 over 2 is -1/2, 1 plus 2 is 3, and 3 over 2 is 3/2. Okay, so there we go. We found the midpoint. By the way, if you wanted to put -1/2, comma 1 and 1/2 instead of 3/2, either one of these answers would be acceptable. Let's see if it makes sense. We go -1/2 and then up 1 and 1/2, right there in the middle. Perfect. I went over a half, negative, and then up 1 1/2. And there it is right there, perfect, right in the middle. Okay, so you do need to know this formula. It is very, very, very important. And a lot of students get this formula confused with, what's the other for? The distance formula, I believe, is the other one. And be very careful with this. Make sure you understand that this is the formula for finding the midpoint between 2 points. You need to know this formula and be able to use it, okay? Now, let's apply this midpoint thought, not the formula, but the thought, to some other math problems real quick. 2 more problems and we'll be done, okay? 2 more. Write this in your notes. I know it's going to take you a minute, but copy this in your notes. B is the midpoint of segment AC. Segment AC has a length of 20. Find the length of segment AB. All right? First of all, I think it would be very wise to get a picture of this. And so I'm going to draw a segment like this. And I'm going to call this right here A. And I'm going to call this C, because it says B is the midpoint of segment AC. So here's segment AC, and then B goes right in the middle. There we go. All right. Now let's continue on. Segment AC has a length of 20. Now that means from here all the way over to here, from point A to point C, is a length of 20. So this whole segment has a length of 20. Find the length of segment AB. Well, students, that should be pretty easy. I mean, if B is the midpoint, then that means B is right in the middle. And if B is right in the middle, then that means AB has to have a length of what? 10. And BC has to have a length of what? 10. So find the length of segment AB. Well, here's segment AB right here. And what is the length of segment AB? 10. That's pretty simple. One more problem, we're finished for the day. B is the midpoint of segment AC. B is the midpoint of segment AC. Segment BC has a length of 8. Find the length of segment AC. This will be a little difficult, or a little different, excuse me. I don't think it'll be difficult. B is the midpoint of AC. So here's point A. By the way, if you want to work ahead, feel free to. Here is C, and B is the midpoint. So B goes right here. Okay? Now, B is the midpoint of AC. That means B is right in the middle. BC has a length of 8. So from B over to C, there's a length of 8. Now hold it. If B is truly in the middle and BC is 8, then from A to B, that segment must also have a length of what? 8. So they're asking us to find the length of AC. So from here to here is 8. From here to here is 8. So the entire segment AC, must have a length of what? 8 plus 8 is 16. Pretty simple, okay? All right, there we go. If you have any questions, don't hesitate to call or email. And I hope this has made sense to you, the study of symmetry, rotational symmetry, and the midpoint formula, and then also finding the lengths of segments using the midpoint.